Welcome to topic 3.7 and 3.8. Today we are learning about solutions. So what a solution is, right? A solution is what's formed when you mix a solute, okay, which is a solid, and it's dissolved in solvent, which is a liquid, okay? And then the key thing is that the resulting solution is homogeneous, meaning the substance has dissolved and you can't actually see it. So a very simple example of a solution would be salt water. So here's a simulation we'll kind of use throughout the lesson today. I'll put a link to this on Canvas, so if you want to play around with it, you can, right? So if I simply add salt to a given solution and it dissolves, right, you can see right here on this graph the concentration, that counts as a solution because I can't see it anymore, but it's composed of those two things, okay? The first thing we're going to talk about is the way in which we measure solutions. And so solutions are measured through a property known as molarity, okay? Its symbol is capital M, and it's a ratio which tells us the moles per liter. Okay, so this is a 2-unit relationship. As you see in our cute little picture here, we have 2 moles in 1 liter. So this would be called a 2-molar solution. Okay. So our equation for molarity, I believe you should have a box in your notes. This equation is on our formula sheet, so we don't need to memorize it, but that molarity is equal to, just like it said there, moles of solute over liters of solution. Okay. All right, let's try a problem together. So this says to calculate the molarity of a solution made by dissolving 23.4 grams of sodium sulfate in enough water to form 125 mils of solution. Okay, now I just want to explain briefly what this little phrase is saying, in enough water. And it's also why on the bottom up here, okay, that it's liters of solution and not liters of solvent. Because by putting, let me draw a little picture here. All right, so if I have a little flask, right, okay, and then I'm putting in my solute, right, which could be like NaCl, okay, that is going to take up some space. It's going to take up volume. And so when we make a solution, we don't add in, right, so we wouldn't add in 23.4 grams of this and 125 mils of water. Okay, we wouldn't do that. We would add this in first. We'd add some water in, so add a little water. Then put in our salt. And then we would add enough water until it gets to the 125 milliliter mark. Okay? All right, so in this problem, the question is we're wanting to find molarity. So molarity, as we said, is moles per liter. So this is a 2-unit thing. So we need to find each of those things separately, and then we can put them together. So step 1 is we're going to find moles. Okay, so they've given us grams. So we're going to convert here. So we're going to take 23.4 grams of our Na2SO4, and we need to convert that into our moles. Okay, so we would go from gram to mole of our substance, and they were nice enough and gave us that number there. Okay, so then we would plug that into our calculator here and take the 23.4 and divide it by our 142. Sorry, I'm stalling because I can't even find the calculator. Okay, so we get 0.165 moles. Okay, all right, step 2 is we need the volume in liters. Okay, so our volume right now is in milliliters. So we do need to convert that. So we have 125 milliliters. And to get to liters, there's 1,000 of them. So we're dividing by 1,000. Or we can just move the decimal 1, 2, 3. So this is equivalent to 0.125 milliliters. Okay, so this is our step 2. And then step 3, okay, is put the moles and liters together for molarity. Okay, so step 3, molarity equals, we're going to take our moles from here, okay, over our volume that we have there, and then plug that. So I'm going to take 0.165 divided by 0.125. And we get a molarity of 1.32. Now the units that can go on this, there's 2 of them. One is you can write mole over liter, okay, or you can write 1.32, just capital M. So either of those are acceptable units, okay? All right, let's take a look at this one. Same topic, it's just we're given different values. So this one says a student wishes to prepare 2 liters of a 0.1 molar solution. Okay, molar is how we kind of talk about molarity. And then we want to know, what is the proper procedure to weigh out mean? Like, how many grams do we need to make this amount? So the difference here is we're looking for our final answer, right? Is we're looking for a gram amount is what we need. So we're still, in a sense, going to use our molarity equation. So molarity is moles per liter. Okay, so if the end goal here is to get to grams, right? If we want to get to grams, then the first step would be get to moles, because moles can connect us into gram. Okay, so step 1 is find the moles. So when you're solving these questions, when it deals with molarity, you're always going to use this equation. It's just the difference is what's going to be given. Last time we were trying to find this. This time we're now trying to find this, okay? So I know my molarity is 0.1, so I'm going to plug that in for M. Okay, and that's equal to, moles is what we're trying to find, over our liters, which was 2. Okay, so that was right here, our liters, that went on the bottom. The 0.1 went over here, and then we're trying to find the mole value. Okay, so if I solve this, we get 2 times 0.1, and so we get that moles are going to equal 0.2. Okay, now step 2, change colors here. Step 2 is convert to grams. Okay, so I'm going to take this 0.2 moles that we found here of our KiO3, and I need to convert that into grams. So mole goes on the bottom, gram goes on the top. Once again, so nice they gave us the mass over 1 times that through, and that will give us how many grams we would dissolve to get the 0.1 molarity. Yeah. Okay, so notice once again that we have 2 different problems in what we're finding. But the basic idea is, once again, identify what you know, identify what you don't know, and then focus on getting the unit that you don't know, okay? All right, for this practice one, I'd like you to go ahead and pause the video and try this one on your own. And when you have an answer, go ahead and hit play and see how you did. Okay, so in this problem here, we're finding molarity. And so in finding molarity, that means we need moles and we need liters. So we're going to find each of those two things separately. Okay, found my moles there. Finding liters is just converting 100 mils, which would be 0.1 of a liter, because remember 1, 2, 3 to the left. Okay, and so then for molarity, let's put it together. So molarity is moles per liter. That's number 1 per liter. And then we just divide them out to get our answer, which would move the decimal over 1. And so that's how we get a molarity of 0.2 molarity of our cobalt chloride. Okay, if you got that right, go ahead and give yourself a smiley face. Homework 3.7, we'll have a lot of different problems like these 3. So if you get stuck on any of those, you can come back and reference these in your notes. Okay? All right, the next we're going to look at here is what goes on when an ionic compound, so keyword here, highlight this, is an ionic compound dissolves. As we learned back in Unit 2 when we talked about ionic substances, when they dissolve, they break apart in the water. Let me show you on our simulation here what's going on. Okay. All right, let me go to a deeper view here. Okay. Sorry, let me see if I can get the screen to be more centered. Sorry, waiting. Okay, so looking here at a deeper level, okay, where we can see the particles themselves. So I'm going to add some salt to my water. Salt is this Na and Cl, right? The sodium is pink, the chlorine is green. And so when I shake it in here, notice they're in clumps, but once they hit the water, they get pulled apart. Due to the fact of the positive and negative ions interacting with the dipoles of the water, which we'll draw a little bit on down the road. Okay, what we're going to focus on right now is that ratio. So notice with the bar graph on the far right, how you have the same amount of Na as you do as Cl because they exist in a 1-to-1 ratio. Okay, so let me remove this one here and we'll go back. Okay, so our equation for dissolving for NaCl would look like this. We would have NaCl. We're going to label it, so we're going to start labeling our equation the states of matter. So I'm going to put a little S next to it. That implies that it's a solid. Okay, now once it dissolves, we're going to draw an arrow to show it the change that's happening. Okay, it's going to break apart into Na plus and Cl minus, and now we're going to label them with a little AQ, meaning aqueous. Okay, our molecular view picture is just going to show that where we have Na plus separate from Cl minus. Okay, for now, what I care about in the molecular picture, okay, is that you have the right ratio of them and the charges. Later on, we'll talk about size because that does also matter. But for our learning at this point, let's just focus on the ratio and the charges. So the ratio is 1-to-1, and the charges are +1, -1. Now, a reminder where charges come from. So charges are connected to valence electrons, right? So if I go to the periodic table, let me draw a rough one here. Okay. Where an atom is located, right, tells us how many valence electrons. And then the charge they form corresponds to whether they're going to lose or gain to achieve that full octet, right? So everything in this column here, right, in column number 1 has 1 valence electron. And then the pattern goes 2, 3, 4, 5, 6, 7, 8. Okay, so valence electrons. So the charge pattern that we have is everything in column 1 will always have a +1 charge because they are trying to lose that 1 they have. Everything in column 2 will have a +2 charge. Same thing here, +3. And then column 4 is we just ignore because those all end up being covalent bonds and never ions. I mean, they don't have charges that we're going to focus on really. Okay. And then after column 4, then a pattern goes opposite of -3, -2, and the halogen family. So column 17 is -1 because these ones don't form a charge because they are always, once again, they don't bond ionically because they have their 8-valent shell, their full valent shell. Okay. All right, let's take a look at this last column here as we focus on the ratio with numbers. So when it comes to moles, remember moles are a counting unit, right? So in a sense, molarity, capital M, is also somewhat related to a counting unit. Now it's moles per liter, right? It's a ratio, but it helps us understand how many of each you have. So if I have a 1 molar solution of NaCl, it's going to break apart into still a 1 molar solution of Na and a 1 molar solution of Cl, okay? Because when, so I'll draw here in this box, right? Before, we counted 1 as the thing clumped together. But then since it breaks apart, I still have a ratio of 1 to 1. So that's why 1, 1, 1. Okay? All right, let's try the next one here as an example. So our next example, let's start with the equation. Okay, so we have Mg3POP2. Okay, so I'm going to write that here. So Mg3P2 is a solid and it's going to break down. Okay, so now the two pieces it's breaking apart to are always the metal and the nonmetal. So we have magnesium, which if I come over here, right, is located in column 2. So I know it has a 2+ charge. Okay, and then that's aqueous now, AQ. And then our phosphorus is located in this column here, right? So it has a -3 charge, AQ. And then finally, what we need to look at here is on the reactant side, right, is it was 3 M's to every 2 P's. And when ionics dissolve, they dissolve apart as much as they possibly can. So what we're going to end up having here is we're going to have 3 of these. Oh, let me make that a pen. 3 of these and 2 of these. Okay, let me show you our simulation to help you visualize that a little bit, and then we'll draw the picture. Okay, I don't have this one in our options, but I have one that we can use at least. Let's use this one. Okay, so notice this one is CaCl2. Okay, so notice when I shake it in, okay, it goes in clumps. But then notice when it breaks down, all the atoms are on their own. They do not stay grouped together. And then if you look at the bar graph on the far right, you can see how there's twice as many Cl's as there are Cas. Okay? So in our case, what we see here is we're going to have 3 times the amount of Mg to the initial 1 that we had, and 2 times, right? So our ratio is, it's a 1 to 3 to 2 ratio. Okay, so if I draw this at the molecular level, what we would have is we'd have 3 Mg's with a +2 charge. Okay, and then we'd have our 2 P- with the 3- charge. Okay, so then in our ratio box here at the very end, okay, we want to list what is the concentration. So if the initial concentration was 2, okay, notice that we had over here, right, for every 1 of these, it's going to make 3 of those. So for every 2, then that means we would have 6 molar for Mg ions. Okay, and then for our phosphorus, okay, our phosphorus is a 1:2 ratio, right? 1:2. So if this is a 2, then this is now a 4. So we would have 4 molar for our P3 minus. Okay, so once again, they're giving you what the concentration is, and then this should reflect the same ratio of how it's breaking up. All right, let's do another one. Okay, so we have Na2SO4. Okay, so let's come back to our simulation here. Let me remove our solute that we have and pick on this one. Okay, so back when we learned about ionic compounds, we learned that sometimes in ionic compounds, there are a group of nonmetals that stay as a group. Okay, so I want you to notice when I put this substance in, it breaks apart, but it's not going to be all individually. Okay, do you see how those orange and blue circles actually stayed intact and they didn't break down into separate circles like our other ones did because they are one of our polyatomic ions. So we had a chart in Unit 2, right? It looks like this in your notes. Sorry, I should have put it in this packet too, but I didn't. But back in Unit 2, you can find this chart that shows you some of the most common polyatomic ions. Once again, we will eventually memorize this, but for now, I will give it to you to use on the test. You can use it while you do your homework just to get familiar with them. Okay, so what this means when it comes to dissolving, okay, is, I'm going to go like this just to give me a little more space, okay, is you're always going to separate it between the positive and negative thing. So it separates always from the metal to the non-metals. And in this case, our non-metals are just going to stay together. Okay, so I'd have Na, which has a plus charge, AQ, plus we're going to keep that SO4 together as one thing. So once again, metals, non-metals. Okay, even though there's multiple things, just keep them together. Now, there's 2 ways you could figure out the charge of this, right, our SO4. One is you could look on the chart, okay, find SO4 and see, oh, it has a -2 charge. The other way is to kind of work backwards from the fact that we know, okay, we have 2 of these that are going to break apart. And if they both have a +1 charge, right, this is +2, and ionics have to be balanced, that must mean that this has a -2 charge. Okay, now for our case, for simplicity, when we show the molecular view, we need to have 2 NAs. But then we're just going to show the SO4 2- as one big thing. Okay, we're not going to draw it as separate little things connected. We don't need to be that detailed because it really is going to stay as a group. So that's how we're going to treat it. All right, looking over here at the ratio. So this tells us it's a 0.5 molarity. Okay, so notice over here that our ratio is, for every one of these, we're going to have 2 of those. So if this is 0.5, then this would be 1. Okay, because it's still a 1:2 ratio. Okay, so we'd have a 1 molar solution of Na. And then for our SO4, right, SO4 for every one of these, we just have 1 of those. So if this is 0.5, then that would also be 0.5. So 0.5 molar of our SO4 2-. All right, let's do one more together, and then I'll have you try some for some smiley faces. Okay? All right, so our last one here is MgCO3. Okay, so to show how it's going to dissolve, you separate the metals from the non-metals. So magnesium is the metal, so we have Mg2+, which means we got another polyatomic here, which is CO3, and it has a 2- charge, AQ. Okay? This example is for every 1, we get 1 and 1, right? So our molarity over here is if it's 3 molar, then you'd still have 3 molar for Mg, and and 3 molar for our CO3 2 minus. And then our picture is just 1 to 1. All right, go ahead and pause the video. Try these ones out. When you think you've got it, go ahead and hit play and you can check your answers with me. All right, here's what we should have gotten. So for this one, you should have gotten that you're gonna have 3 Na plus and PO4 3 minus is its charge. Okay, which means in our picture we got 1, 2, 3 for every one of these. And so then my ratio would be, since it's a 1 molar and there's 3 times the amount of sodium, so it should be 3 molar for Na plus and 1 molar for PO4 3 minus. Go ahead and you can have 1 smiley face. If you got this right, you can have a 2nd smiley face if you got this right. All right, let's do the next one. Okay, LiCl is going to break up into a 1-to-1 ratio. So we just get Li plus Cl minus. Once again, these two things, right, this column and this column are showing you the same thing. I'm just once again trying to help you connect the whole chemistry triangle together, right? That this is the symbolic side and this would be our molecular view side, okay? All right, so then since it's a 0.125 and we have a 1-to-1-to-1 ratio, then that means it's 0.25 for Li plus and 0.25 for Cl minus. Going ahead and once again have a smiley face for this being correct and a second one for this one. All right, last one here. Okay, aluminum bromide would separate into Al3 plus and 3 Br minuses. Have a smiley face if you got that right. And then your picture should have 1 of those and 3 of these. Okay, so if it's a 0.125 molarity, then it'd be not 125, 0.25, then it'd be 0.25 for aluminum. And because the Br, right, we have 3 times the amount of it compared to the aluminum. So 0.25 times by 3, which gives us a wrong button, 0.75 molarity for Br minus. Go ahead, once again, have up to 2 smiley faces for getting that correct. All right, here's really what we just did. It's just, this is maybe how it could be phrased on the AP exam, where it says we have some solid aluminum nitrate is added to distilled water to produce a solution in which the concentration of the nitrate is a 0.1 molar. What is the concentration of the aluminum ion? So being that we're dealing with the creation of a solution, if it isn't given to me, I would always write out, just like we did up above, that equation. So we'd have this as a solid, and then if I break it apart, okay, that's going to give us Al, which has a 3 plus charge. And then notice once again right here, okay, so remember we separate the metal, so here's my metal, and then we keep the non-metals together, okay? So then we would have NO3 minus, and this little 3 that's outside the parentheses would come in front because those would then break apart from each other. So the NO3s would separate from the other NO3s, okay? So then what the question is saying is it's telling us that we have a 0.10 molar of this. What would the concentration of this one be? And so since it is a 3 to 1 ratio, that means I have 3 times the amount of my NO3. I'm just going to take 0.1 and divide by 3. And so the concentration, I'll write that out. So So this is, we're taking the 0.1 divided by 3 because of the 3 to 1 ratio. And so we get that the concentration would be 0.03 molarity for our Al3 plus ion. So hopefully you see the similarity between this question and all these ones we just did. It just kind of gives it to you in the AP way of wording things. Okay, next thing here is dilutions. So what it means to dilute something is it simply means we're going to add water, okay? By adding water, you are lowering the concentration. Okay, so the idea of a dilution is to go from a high to a low concentration by simply adding water. So if you look here at our picture, okay, so here's before the dilution, okay, and notice the concentration. So the triangles represent the moles, the circles represent the water, okay? If I simply just add more water, then the concentration goes down because the ratio has changed, right? You have more water with the same amount of solution, okay? Or solvent, I should say. The key thing is that the number of moles does not change. So the way we can look at this in terms of a mathematical equation is that the molarity of the diluted solution, change that. Okay, the molarity of the concentrated solution times by the volume of the concentration solution will equal the molarity of the diluted solution times the volume of the diluted solution. It's a proportionate relationship of how adding water will keep the moles unchanged. Okay, in this whole beaker, this beaker and this beaker would have the same amount of total triangles, but since molarity is moles per liter, right, this one has a lower molarity. All right, let's try a problem. Okay, so this one says, what volume of a 0.1 molar solution is needed to prepare 250 mils of a 0.1 molar solution of our copper sulfate? So the key thing here is we want to identify what is our MCVC and our MDVD, right? So what is being diluted? What is the concentrated side? Okay, so our concentrated side is always going to be the high molarity. So since we're going from, let's get a highlighter here. Okay, so since we're going from a 1 molarity down to a 0.1 molarity, right? This would be my diluted and this would be my concentrated. Okay, and then when I read it here, it says needed to prepare 250 of that. That tells me, okay, this volume corresponds to how much of the diluted volume I need. And so this is my unknown variable. Okay, so let's set up our equation. So MCVC, MDVD, let's plug in what we know. Okay, so we got 1 molar, right, for this. V of C I don't know, so we'll just leave that as a variable. And then we have 0.1 molar here, right? And 250 milliliters there. Okay, right? So that came from here. That came from there, right? Okay, so then to solve this, okay, we would just, in a sense, divide both sides by 1 molarity to get the V on its own. And so then we get the volume of the concentrated would end up being the 0.1 times the 250 divided by 1, which gives us 25 milliliters. Okay, now quick note here, I forgot to mention, we didn't have to change our unit of milliliter We could have changed it to liter, but if we keep it in milliliters, then that's how we end in milliliters. So that's kind of what this note was saying, is that any volume of unit can be used as long as it's the same on the both sides. So both liters, both milliliters, as long as they match, it will work. Okay? All right, try this practice problem with your table or on your own, and then pause it and then hit play to check and see how you did. All right, so there's my setup, plugging in my concentrated and my diluted values, plug it into my calculator. I probably should have mixed up a little bit and give you one slightly different, but hopefully you're seeing how this equation works together. So we have 0.05 times 50, dividing it by 0.1. All right, so I'll show that here. So divide that by 0.1. Divide that by 0.1, plug it into your calculator. And wow, look at that. It's the same answer as before. So if you got 225 mils of our 0.1 copper sulfate solution that we would need, go ahead and give yourself a smiley face because you're correct. So once again, on the second half of homework 3.7, you'll find some dilution type problems. So once again, you can come back and reference these if you need help. All right, our last topic is just diving a little bit more into the molecular view of what's going on with the interactions with water. So first thing, we've mentioned it before in Unit 2, that when ionic substances dissolve, they conduct electricity. The chemical name for a substance that can do this is an electrolyte. An electrolyte breaks apart into ions, and so then it can conduct. A substance that doesn't form ions is called a non-electrolyte. So let me go back to our simulation here. Okay, so if I add our conductivity meter here, okay, if I add salt to my water, then we can see our little light bulb beginning to glow, because salt is an ionic compound, and so it breaks apart, as we saw, into positive and negative things, okay? Versus, let's get rid of the salt, if I put in sugar, which sugar is a covalent compound, it still dissolves, but notice the light bulb does not light up, okay? So let's go a little molecular here, actually clear this out, okay? So we saw our salt, but let's look at sugar here. So the key thing here is that when sugar goes into water, so notice they're in big clumps here, and when it dissolves, it does break apart, but it still stays in a pretty large group because it's still staying in that C12H22O11. It doesn't break down any further. You do not get positive and negative ions. Okay, so an ionic compound dissolves, the ions separate, and the water helps stabilize the ions and prevent them from combining. So let's go ahead and draw on these pictures the interaction that these molecules would have with water. Okay, so our first one here is our ionic example. Okay, so just like we did before, ionic would break apart, so we'd get 2 Na pluses, which is already shown to us. Oh, why did I draw an arrow there? Okay, plus SO4 2 minus, which is aqueous. Okay, I showed it to you as like, here's your S and this is your 4 O's. But once again, when you draw it, if you just want to draw it as one full circle, right, and just label it as SO4 2 minus, that is just fine. Okay. All right, so let's talk about water, right? So we learned back in Unit 2, right? So water is good old H2O. Okay, here's its Lewis structure. Okay, we then learned that it actually looks like this because those lone pairs at the top cause it to be a bent shape. Okay, then we learned that water is very polar and has high intermolecular forces. due to the fact that this water is pulling the electrons up, resulting in, right, once again, we would have a positive side down here and a negative side up top, okay? So the way that water interacts with our molecules should follow this suit, right? Where once again, the oxygen is the negative side, the hydrogen is the positive side. Now, you can draw water two ways. You can draw it just like this, right? Just like we showed. Okay, you could draw it that way, showing the individual O's and H's. Another way we often draw it, which you will see like on my answer key, is by showing water to look like this. Okay, where this centerpiece, right, this is your oxygen. So this is oxygen, and then these are our two hydrogens. If you flip that around, that's why we sometimes people will say water is like Mickey Mouse. Okay. Key thing is once again, these up here. Oh, right. These are my positives, and this is my negative. Okay, right. So positives and negative. So when I show the interaction with water in my picture, so looking back over here, okay, since this is my positive sodium, when water interacts with it, right, opposites attract, we need to show the water attracted from the oxygen side of it. I'm going to use two different colors just to help emphasize that point, okay? I'll just draw two little ones there to represent it. Obviously, it would truly be like completely surrounded, right? So there'd be waters all around it. But for simplicity, we'll just show two. Okay, so let's draw the same thing here because it's positive. So we need the negative oxygen would be the side interacting with it. Okay, but then since this compound is negatively charged, we're going to see the opposite. Okay, so in this case, we're now going to see, the positive waters, or the ears of our Mickey Mouse, are going to attach to the negative ion. And that, in a sense, is how it dissolves. Okay, come back to our simulation so you can see that at a little deeper level. Okay, so here's all our little waters. If I add in our salt compound, you'll see how it breaks apart. And if you focus on, like, notice how they're interacting with the chlorine versus how they're interacting with the sodium in that orientation of the water, okay? So that orientation of the water is very important, right? There's our positive and negatives, okay? All right, now looking at sugar. So sugar is, I'm going to erase some of this just to give me some space. Okay, so sugar is a covalent compound that does dissolve. So as we learned with intermolecular forces, it's dissolving because of the interaction of the IMFs. The difference is that when this substance dissolves, it doesn't break down. It still stays as C6H12O6, but now we call it aqueous. So once again, notice over here, we separated, right? So we separated the metals from the nonmetals. But in this case, they're all nonmetals, and so all the nonmetals stay together. And so that's what this right here, it's showing you the giant structure for our sugar, and it's not breaking down. But we are going to draw the interaction with water that's going on here. Now, in this case, because it's interacting as an intermolecular force, hydrogen bonding, I'm going to do the dashed line idea. Okay, so I'm going to draw right here with this hydrogen. We can draw a dashed line and show the interaction with water, focused on, right, that the interaction happens from the H to the O. Okay, obviously there'd be a bunch of them because there's a lot of sites for hydrogen bonding, but we're just going to show one there. I'll show one on this molecule right on this side. You could have a hydrogen bond there. Okay, like so. Okay, this interaction, by the way, with our salt is actually considered a fourth type of intermolecular force known as an ion dipole force, because the dipole is the water and the ion is the salt. All right, let's end with one practice exercise here. Oh, I was going to show you on the simulation really quick. Whoop. Let's get rid of our salt. Okay, so I'm going to add in a sugar molecule. Okay, so notice that there's two molecules clumped together. When it goes into the water, they separate into two different things. And if you look closely, you can somewhat see, once again, how those positive and negative interactions can form those hydrogen bonds there. So, but it stays clumped as one giant group. All right, so this says beaker X and beaker Y each contain 1 liter of solution. A student combines the solutions by pouring them into a larger previously empty beaker and observes the formation of a white precipitant. Okay, assuming that the volumes are additive, which of the following sets of solutions could be represented by the diagram above? Now, we're going to learn more about precipitants in Unit 4, but that just means you have a solid in the bottom, which is what this little clump is representing. Okay, this sentence right here, assume the volumes are additive, is saying that this beaker would now have, well, that's a weird arrow, okay, would now have 2 liters because these were both 1. Okay, normally volume isn't perfectly additive. Okay, so what they're saying is we want to see which would be the correct molarities. Okay, so molarity is moles per liter. Okay, so moles, right? Moles we can count. Okay, so if I look in this first beaker here and I count up my ions, hopefully I can count them. I have a weird thing that copied over with my picture. Okay, but we have 1, 2, 3, because I'm counting them as the solid they are, right? Because that's how it's asking to be measured. Okay, 1, 2, 3, 4, 5, 6, 7, 8. I believe there's 2 more down there. 9, 10. Okay. In this one, it's MgCl2. And so if I group it back together, you got 1 Mg to 2 Cl. So there's 1, 2, 3, 4, 5. Okay, so in this one we have 10, in this one we have 5. Okay, so that means the concentration, because the concentration is moles per liter as a ratio. Okay, so this beaker right here, this tells me that this one should be twice as concentrated as this one. So if I look through my answers, I can cross off A, because A has them equal 2 to 2. Cross off B, can't be that one. So C and D are both plausible because it shows me there's 2 to 1, right? 10 to 5, 2 to 1. So then the last part is, okay, what's going to happen to the concentration of the MgNO2 in the final beaker? So let's do some counting there. So once again, MgNO2, so I'm going to group them back together. Okay, so 1, 2, 3, 4, 5. Okay, so this has 5 moles, but remember, twice the volume. So we have the same concentration, but it's going to get cut in half. And so that's how I know it's answer D, because my ratio is, right, 2 to 1 to 0.5. If I look at 10, 5, and in a sense, this would be like changing it to 2.5. All right, that's it. Go ahead and try out the homework to put this all together. I know it's a lot, and so homework's the best way in which it can give your brain chances to go slow, right? Connect those pieces so then we can eventually do these things quickly. All right, good luck.